The mole. What, why, and how. This is preparatory for a second-year chemistry class. So we'll look at the question. If 1.0 grams of hydrogen gas will react with exactly 18.99 grams of fluorine gas, how many grams of chlorine gas would react with that same amount of hydrogen gas? Well, the answer is the reactions are almost identical. Fluorine and chlorine will both react explosively with hydrogen. They're both halogens, highly reactive. But from the data we're giving here, and only this data, we could not predict the amount of chlorine which would react with 1.0 gram of hydrogen, even if we know how much fluorine will react. Why not? The unit of chemical quantity is not a mass unit. Different masses of different but similar chemicals will react with the same amount of another chemical. But we can rely on the fact that chemical reactions all involve a predictable number of atoms of each element reacting with a predictable number of atoms of the other element. So let's look at this particular reaction. One molecule of fluorine reacts with one molecule of hydrogen to form two molecules of hydrogen fluoride. We have a visualization here of the one molecule of hydrogen on the left and the one molecule of fluorine on the right about to react. They haven't collided yet. Now they collide, and after the collision, we have two molecules of hydrogen fluoride, as predicted. Now, if we change to the different halogen, to chlorine instead, we know that one molecule of chlorine reacts the same way with hydrogen. One molecule of hydrogen reacts with it to form two molecules of hydrogen chloride. Here are the molecules of hydrogen and chlorine before the reaction, before the collision, and after the collision and reaction, there is your hydrogen chloride molecules, two of them. So what we need is a chemical unit that tells us how many atoms or molecules we're working with. From that, we can predict how many atoms of the other reactant are needed, and from that, we can get how many molecules or units of the product would be formed. Let's see how that works. The unit of chemical quantity is the mole. It's a given number of atoms or molecules. The abbreviation is MOL, and you say, what kind of abbreviation is that? Well, it's 25% shorter, so it is a more efficient way of writing it. For most of our work, we will use less than a mole, so we tend to measure in millimoles. And now, the abbreviation MMOL is 60% more efficient because we knock out 6 letters. The mass of a mole of any element can be found on the periodic table. We'll take that for granted for the time being. Here is the IUPAC, International Union of Pure and Applied Chemistry, periodic table of the elements. And this is from 2016. This is copyrighted. The mass of 1 mole of any element is found on the periodic table. For instance, the hydrogen atomic mass is 1. The fluorine atomic mass is, in round numbers, 19. And for chlorine, we've got 35.5. All of those are measured in grams per mole. So we now have a conversion factor of grams per mole. Now keep in mind, hydrogen gas is diatomic. It comes in packages of 2. That's also true of nitrogen, oxygen, and all the halogens. Make sure you remember that when you're working with the elements. In those cases, in those 7, you're working with diatomic elements. So you have to multiply the mass of the atomic mass You have to multiply that by 2 to get the molecular mass. All right, let's see about problems. We can translate now moles to grams and grams to mole. So 1 mole of hydrogen gas reacts with 1 mole of either fluorine gas or chlorine gas. This is fluorine's reaction shown. And that's because 1 molecule of hydrogen gas will react with 1 molecule of either fluorine or chlorine. So this can either stand for the balanced equation for 1 molecule of each or for 1 mole of each. Now, can we translate that to masses, which is something we can measure in the lab? Of course we can. We have the atomic mass table from the previous slide. So, to translate grams to moles and moles to grams, here is one of our reactions. Hydrogen and fluorine gases react to form hydrogen fluoride. 1 mole of hydrogen here reacts with 1 mole of fluorine to form 2 moles of hydrogen fluoride. Now, 1 mole of hydrogen atoms is 1 gram. Since hydrogen is diatomic, 1 mole of hydrogen molecules must be 2 times 1 gram per mole, or 2 grams of hydrogen gas per mole of hydrogen gas. And 1 mole of fluorine atoms is 19 grams, but it's also diatomic. Therefore, 1 mole of fluorine molecules must be twice that, or 38 grams. Thus, 2 grams of hydrogen, that's 1 mole, will react with exactly 38 grams of fluorine, 1 mole, and the law of conservation predicts that 40 grams of hydrogen fluoride will form in that reaction. Looking at the other halogen we've been talking about, hydrogen and chlorine react to form hydrogen chloride gas. 1 mole of hydrogen reacts with 1 mole of chlorine to form 2 moles of hydrogen fluoride. Now, 1 mole of hydrogen atoms is 1 gram. And since hydrogen is diatomic, 1 mole of hydrogen molecules must be 2 grams, just like it was before. And 1 mole of chlorine atoms is 35.5 grams, and since chlorine is also diatomic, we have to see 1 mole of chlorine molecules must be 71 grams. Thus, 2 grams of hydrogen will react with 71 grams of chlorine. And the law of conservation predicts then that 73 grams of hydrogen chloride will form. We could do the same with bromine or iodine. And just for the sake of argument, let's look at the reaction. Most of these are snips from YouTube. Reaction of hydrogen with fluorine, chlorine, bromine, and iodine. So now let's do a little stretching here with you and let you solve some problems. This is your turn. Determine how many grams of bromine would be needed to react with 3.0 grams of hydrogen gas. See if you can set that up. Turn this video off, and then turn it back on when you've got an answer. Well, grams of bromine, of course that's Br2, would be equal to 3 grams of hydrogen. Now, we want moles of hydrogen. We always go in what we call the mole hole. So we multiply by the conversion factor. 1 mole of hydrogen is 2 grams. Now, we look at our balanced chemical equation and see from it that 1 mole of bromine reacts with 1 mole of hydrogen. So, this now converts us from hydrogen moles to bromine moles. And then finally, we want to know grams of bromine. So we look at the table, multiply the molar mass of bromine by 2, and we get 160 grams of bromine Br2 per mole. When you do the canceling of terms, grams of hydrogen go away, moles of hydrogen go away, moles of bromine go away, and we're left with grams of bromine, 240 grams of bromine. Now let's determine the same thing for iodine reacting with 3.0 grams of hydrogen gas. Turn the video off, do your work, and then check the answer. grams of iodine would be 3 grams of hydrogen. Now we're going to go first into the mole hole, and because there's 2 grams of hydrogen in a mole, change this to moles of hydrogen. It'll be 1.5 if you stop at that point. Then we look at the balanced equation and see that 1 mole of hydrogen produces 1 mole of iodine. Then we multiply that by the molar mass of iodine that takes us out of the mole hole. And now grams of hydrogen cancel, moles of hydrogen cancel, moles of iodine cancel, and we're left with grams of iodine as our answer, 381 grams of iodine. Now, how did we get those molar masses? We're going to have to wait on that. Exactly how chemists determined accurately the atomic mass of all those elements is a fascinating tale of chemical history, and we're going to look at that in a little depth in the AP Chemistry class.